Hello students, welcome to this session. In this session, we discuss the joint probability distribution of random variables, in particular with respect to discrete random variables. Joint probability means it is the probability of occurrence of two or more events simultaneously or together. Suppose if we consider two events, say A and B, then the joint probability of the two events A and B is denoted as probability of means P of A and B, means it is P means probability of A intersection B. Generally the intersection stands for the simultaneous or the occurrence together. Therefore, the joint probability of two events A and B is denoted as P of A and B, and it is equivalent to probability of A intersection B. That's the way we can do it. In order to understand the concept of joint probability, now let us go with one or two examples, simple examples. Suppose if you want to find the probability of getting a head and a number 4 when we toss a coin or flip a coin and a roll a dice together. Means when we toss a coin and roll a die together, and if you are interested to know what is the probability of getting head and a number 4, then how we have to proceed? Let us see that. Now let's define two events A and B. Let us say A as probability, means A as getting a head when a coin is tossed, and B as getting a number 4 when a die is rolled. Then probability of the event A means probability of getting head when a coin is tossed is given by 1 by 2, because whenever a coin is tossed there is a 50% chance of getting head. And probability of B means probability of getting a number 4 when we roll a die. Means when we roll a die there are 6 possibilities. Out of 6 there is one possibility which is resulting in the favorable one, that is getting a number 4. Therefore probability of the event B is given by 1 by 6. Now consider the joint probability, and that is nothing but probability of getting head and a number 4, that is probability of A intersection B. And now we know that the two events of tossing a coin and rolling a die are independent. Therefore probability of A intersection B equals to probability of A into probability of B. By the definition of independent events we can write this, and that is equals to probability of A is 1 by 2 and that of probability of B is 1 by 6. Therefore the total probability is given by 1 by 12. Therefore this 1 by 12 represents the probability of getting head and a number 4 when we toss a coin and roll a die simultaneously or together. That's one simple example which illustrates the concept of joint probability. Now let us go with one more example of that kind. Suppose if you want to find the probability of getting sum as 12 when we roll two dice at once or two dice together. Now one thing is very clear that we get the sum as 12 only when both the dice shows the number 6. That's one thing is very clear. In all the other cases the sum is never equals to 12. That's why let us say one event A as first dice shows in number 6 and B as second dice shows number 6. Now probability of A, again when we roll a die, therefore total 6 parties over there. Out of 6 possibilities, one possibility is going to be occurrence of the number 6. That's why probability of A equal to 1 by 6. In the same fashion, probability of B is also equals to 1 by 6. Now let us consider the joint probability. Here the joint probability is we want probability of getting the sum as 12. This happens only when the first die should show 6 as well as means, and the second die also shows a number 6, and that is given by again probability of A into probability of B, because rolling of two dice both events are going to be independent. That's why we are going to say that is, as we defined, A as first die shows number 6 and B as second die shows number 6. These are independent events. That's why we can write probability of A intersection B equals to probability of A into probability of B. And we know probability of A is 1 by 6 and probability of B is also 1 by 6. Therefore, it results in 1 by 36. And this 1 by 36 represents the probability of getting the sum as 12 when we roll two dice at once. We get the sum as 12 only when the first die shows number 6 and the second die also shows number 6. That's the probability of getting 12 whenever we roll 2 dice at once to get the sum as 12. Now, in order to understand the concept still in a better way, let us consider an example. That example states that consider a survey conducted for 1,000 individuals to know their favorite sport, and the following data is collected. And one survey is conducted in which the individuals are 1,000 individuals are inquired regarding their favorite sport, in order to know their favorite sport. And it is very clear that there are 1,000 students, or sorry, 1,000 individuals are inquired, means 1,000 individuals are participated in the survey, out of which 530 are males and 470 are females. That is one more thing. And now this 150 represents 150 males whose favorite sport is cricket. 250 females says that their favorite sport is cricket. In the same fashion, 300 and 120 are saying, male and females are saying their favorite sport is soccer. Similarly, 80 males and 100 females are saying that they are having other as their favorite sport. And once you take the sum, this 400 represents the total number of individuals irrespective of their gender. They says that their favorite sport is cricket. Similarly, 420 individuals says that irrespective of their gender, their favorite sport is soccer, and 120 individuals irrespective of their gender says that they have other sport as their favorite one. Therefore, there are totally 1,000 individuals participated in the survey, and this is the data we obtained. Now let us divide every element or every number in the table by 1,000. Then we get, once we divide this one by 1,000, we get 0.15, 0.25, 0.4, 0.3, 0.12, 0.42, 0.08, 0.1, 0.18, 0.53, 0.471. These are the values what we are going to get when we divide every number in the table by 1,000. Now let us know what these numbers represent. Therefore, this represents 15% of the males says that their favorite sport is cricket. Now this 25% or 0.25 says that female says that their favorite sport is cricket, and this zero point 0.3 or 30% male says that their favorite sport is soccer, and 12% or 0.12 represents that the 12% of the female says that their favorite sport is soccer. In the same fashion, 8% of the males and 10% of the females says that they have other sports as their favorite. And this 0.15, and this represents the probability that the individual is a male whose whose favorite sport is cricket. That's why this is going to be called as joint probability, and this is a joint probability that represents probability that the individual is a male and whose favorite sport is cricket. That's why it is equal to probability of male and cricket, and that one equals to 0.15. In the same fashion, 0.25 represents the probability that the individual is a female and whose favorite sport is cricket. In a similar fashion, we say that 0.13 is the probability that individual is a male and whose favorite sport is soccer. In the same fashion, we can claim the rest of the values, and we have shown here. Okay, therefore these represents joint probabilities. These 0.15, 0.25, 0.3, 0.12, 0.08, 0.1, these are going to be called as joint probabilities. Once you sum these, therefore 0.15, 0.25, that represents 0.4, and similarly this represents 0.42, this represents 1.8, and this represents 0.53, this represents 0.47. And what this 0.4 stands for? This 0.4 stands for the probability that 40% of the individuals like cricket, or 40% of the individuals having their favorite sport as cricket, irrespective of their gender. Similarly, 0.42, okay, this represents that the 42% of the individuals like soccer and 18% like other sports, and this 0.4 represents probability of cricket. That is, this 1.4 is called as marginal or individual probability. This is the individual probability for cricket, and this is the individual probability for soccer, and this is the individual probability for other sports, and these are representing marginal probabilities. In the same fashion, once you take, these are about row totals, once you go for column totals, therefore the column totals is 0.53 and that is 0.47. This 0.53, or we can say that 53% of the males are took part in the survey, and similarly 0.47 or 47% of the females took part in the survey, and these are also called as marginal probability. These are the marginal probabilities with respect to sports, and these are the marginal probabilities with respect to sex or with respect to gender. And here it is very evident that once you take the total of marginal probability, it is going to be 1. Either you take marginal probabilities with respect to sports, it is going to be 1. And if you consider marginal probabilities, total of marginal probabilities with respect to sex or gender, it is also equals to 1. Now, as we told that here also, these values represents the joint probabilities, and generally these joint probabilities are denoted by P of xy. And before that, let us say, or let us denote sports by the variable x and the sex or a gender as variable y. In this case, x can take three values, namely cricket, soccer, and others, and y can take two values, one is male and one is female. And these joint properties are denoted by P of xy. That is, P of xy means it is the probability that the random variable capital X takes the value small x and the variable capital Y takes the value small y. And these are called as joint probability, means probability that the capital X, the variable capital X takes the value small x and the variable capital Y takes the value small y. And again, once you consider these totals, the probability means the total of the probabilities of joint probabilities, it is going to be again total is 1, or we can say that sum of the joint probabilities is also equals to 1. And one thing, and what this 0.15, this 0.15 represents the probability that capital X takes the value cricket and capital Y takes the value male. Similarly, this 0.1 represents the probability that the capital X takes the value others and capital X takes the value others and the variable capital Y takes the value female. Like that, this 0.13 represents the probability that the variable capital X takes the value soccer and the variable capital Y takes the value male. In this fashion, we can claim all the other things. Here also, we can conclude the one important thing that, therefore, you can look at each joint probabilities, and what you have denoted this one by one pink color, that each joint probabilities are non-negative. Therefore, they are greater than or equal to 0, and once you sum these, their total is going to be sum. That's why here we have written that sum of the joint probabilities is always equals to 1. And these things that what you have written 0.4, 0.1, 0.4, 0.4 to 0.18, these are called marginal probabilities with respect to sports or with respect to the variable x, and these 0.53 and 0.47, these represents the marginal probabilities with respect to gender, and this total is called as P of y and this total is called as P of x. This is marginal probabilities of a variable x, means with respect to sports, and these are marginal probabilities with respect to the gender, that is male or female, that is with respect to sex we can claim this. Therefore, this example illustrate what are joint probabilities and what are marginal probabilities, and what is the nature of the joint probabilities, and what is the nature of marginal probabilities. Marginal probabilities are also called as individual probabilities, we can say. Now, instead of going with respect to examples, let us define them in general. In order to define the joint probabilities in general, let us consider two discrete random variables, say x and y, because our study is restricted to the discrete random variable. Therefore, in order to define the joint probability distribution in detail, okay, or in general, let us consider two discrete random variables x and y, where x takes the values x1, x2, so on, xm, and y takes the values y1, y2, so on, yn. Then the probability of an ordered pair xy is denoted as P of xy and is defined as follows. That is, P of xy equals to P of means probability that the variable capital X takes the value small x and the variable capital Y takes the value small y. And the same thing is written as probability that capital X equal to small x intersection capital Y equal to small y, where the small x takes any values from the list x1, x2, so on, xm, and small y takes any of the value from the list y1, y2, so on, yn. Now, whatever the function we have defined as P of xy in equation 1, it is called a joint probability mass function if it fulfills or if it satisfies the two conditions. The first condition is P of xy is greater than or equal to 0 for all xy. Means whatever the values the variable capital X and capital Y take, for each value P of xy must be non-negative. That is the first condition. And the second condition is double summation of P of xy equals to 1, where one summation is on y and another summation is on x. The second one can be easily remembered as the total of all the joint probabilities must be equals to 1. Whenever the function P of xy satisfies these two conditions, then that function is called as joint probability mass function. Now, generally, the joint probability distribution of two discrete random variables x and y is denoted by the following table. As we have considered that x takes the values x1, x2, so on, xm, they are listed here. That is x1, x2 in general xi, and last one is xm. And y takes the values y1, y2, so on, yn, and we are going to be listed here as yn, y2, yj, and so on, yn. Now this p of x1, y1, okay, as we have defined here in general P of xy, it is the probability that the variable capital X takes the value small x and the variable capital Y takes the value small y. In the same fashion, P of x1, y1 refers or represents the probability that the variable x takes the value x1 and the variable y takes the value y1. Now P of x1, y2 is represents the probability that the variable x takes the value x1 and the variable y takes the value y2. In general, P of xi yj represents the probability that the variable x takes the value xi and the variable y takes the value yj. In the similar fashion, we can define all other probabilities. And now, before that, let us know one more thing. These joint probabilities sometimes also be represented by P11, means it's the probability that x takes the value x1, y takes the value y1. Similarly, P12 means it is the probability that x takes the value x1, y takes the value y2. Like that, P11, P12, P1j, P1n, like that, the joint probabilities also can be represented in general like this, where Pij represents the probability that the variable x takes the value xi and the variable y takes the value yj. Now let us consider each row total first. Now let us denote the total of the first row by P of x1. Let us denote the total of the second row as P of x2. Let us denote the ith row total as P of xi. Let us denote the mth row total as P of xm. And each of these P of x1, P of x2, P of xi, and so on, P of xm, these are called marginal probabilities of x, where P of x1 represents the probability that the variable x takes the value x1. P of x2 represents probability that the variable x takes the value x2, and so on. P of xm represents the probability that the variable x takes the value xm. In the same, and one more thing, we add these P of xi, that is marginal properties of xi, definitely it results in the total 1, as we have discussed here. Either you go for row total or you go for column total. In both the cases, the total is going to be 1, and the same thing can also be observed here. Now let us go for the column totals. Now let us jot the total of the first column as P of y1 and the second column as P of y2, the jth column as P of yj, and the column of nth total of nth column is P of yn, where P of y1 represents the probability that the variable y takes the value y1. P of y2 represents the probability that y takes the value y2. P of yj represents the probability that y takes the value yj, and so on. P of yn represents the probability that y takes the value yn. And each of these P of y1, P of y2, so on, P of yn, they are called as marginal probabilities of y. And here also the marginal properties, total of marginal properties also equals to 1. And one thing is very clear here, if you add all the joint properties, its total is 1. If you add all the marginal properties of x, it is equals to 1. If you add all the marginal properties of y, then also it is equals to 1. This is the table which shows the joint probability distribution of the two discrete random variable x and y, where x takes m values, namely x1, x2, so on, xm, and y takes n values, namely y1, y2, so on, yn. Now, before going to the examples, we must know some more definitions which we are already familiar when we are discussing the third model on random variable and probability distribution. And the first one of them is expected value of x. It is defined as the summation of x into p of x, means it is a total of x into p of x, and expected value of y is, it is a total of y into p of y, that is summation of y into p of y. And one new thing, that is expected value of xy, and is defined as double summation x into y into corresponding joint property p of xy. And in general, it is defined as, it is the product sum of all the possible values of x, y, and corresponding joint probabilities. And we can discuss in detail when we are solving the example there. Let us concentrate how to calculate expected value of xy for a given joint distribution in detail. And next, expected value of x square, it is also familiar in the third model. It is given as a summation of x square into p of x, and expected value of y square as summation of y square into p of y. And now this is covariance of xy. This is denoted as COV of xy, and it is defined as expected value of xy minus expected value of x into expected value of y, where expected value of xy is given like this, and expected value of x and expected value of y are given in this way. Next, let us go for one more thing which we are already familiar in the fourth module, that is correlation coefficient, that is R, where we have calculated the correlation coefficient for a set of numerical data. Here the same thing has to be calculated based on the probability approach. That is, again, there will not be any change in the definition. That is, correlation coefficient of R is given as covariance of xy divided by standard deviation of x into standard deviation of y, where The covariance of xy is defined like this, and standard deviation of x is given by it is square root of expected value of x square minus expected value of x whole square, and standard deviation of y is given by square root of expected value of y square minus expected value of y whole square. And two more important definitions. One is marginal distribution of x and one more is marginal distribution of y. Now, in the third module, we have defined that the probability distribution means it is a systematic representation of the values taken by the variable with corresponding probability. By using that concept, the marginal product distribution of x means first we have to list out the values taken by x and their corresponding probabilities. Once we refer this table, we can conclude that the values taken by the variable x are x1, x2, so on, xn, and that we have written here. The values taken by x are x1, x2, so on, xn. Next, we have to list out the corresponding probabilities. Looking at this table, the corresponding properties are given by P of x1, P of x2, so on, P of xm, where P of x1 is the total of the first row, or it is the total of the values in front of the value x1 that we have written here. In the similar fashion, P of x2 is the probability that the variable x takes the value x2, okay, that we have written here, and so on. In general, P of xm represents the probability that the variable x takes the value xm, which is nothing but the total of mth row, or it is the total of the values in front of the value xm. Okay, that's the marginal probability distribution of the variable x, and once you look at the total of that, again it results in 1. Similarly, we can list out the marginal distribution of y, and once you look at the table, we find that the values taken by y are y1, y2, so on, yn. That's why first you have listed the values taken by y1, y2, so on, yn, y as y1, y2, so on, yn, and the corresponding probabilities are nothing but the totals in front of those values, namely p of y1, p of y2, so on, p of yn. That we are written p of y1, p of y2, so on, p of yn. And again, its total is going to be 1. Now, one more important note that is with respect to independence of the variables that we have to discuss. And these concepts are similar to the concept of independent events in the probability theory. We know that the two events A and B are independent if probability of their intersection equals to product of their respective probabilities. In the same fashion, if the variables x and y are independent, we can write P of x, y is given by P of x into P of y, and the expected value of x into y is given by expected value of x into expected value of y. And we can rewrite the covariance expression whenever the variables x and y are independent as follows. We know that covariance of xy is given by expected value of xy minus expected value of x into expected value of y. And when x and y are independent, we can write expected value of xy as expected value of x into expected value of y. Once if I replace by its equivalent, they get cancelled, it seems to be 0. That's why we conclude that whenever the variables x and y are independent, the covariance term becomes 0. That will be the conclusion we can draw. And with this consequence, we can draw one more conclusion, that we know that the correlation coefficient R is given by covariance of xy divided by standard deviation of x into standard deviation of y. When the variables x and y are independent, the covariance term becomes 0. Hence, the R value also becomes, means numerator is 0, and they divided by some denominator, again it results in 0. Therefore, we can conclude one more thing which is not listed here, that if the variables x and y are independent, the first thing is covariance term becomes 0, and another term, correlation coefficient, is also 0. In this particular video, we have discussed some of the basic concepts of joint probability distribution, what are joint product distribution, what are their nature, what are marginal distributions or individual distribution, how we can compute them, how to calculate expected value of xy, how to calculate covariance, how to calculate correlation based on probability approach, and so on. In our next video, let us concentrate on the examples based on the joint probability distribution. Thank you.